Every year, the world produces over 5 million tons of structural steel, and almost all of it is born from rusty scrap. Old cars, dismantled ships, demolished bridges get melted down and transformed into I-beams, the steel backbone of modern cities. From the outside, it looks simple, a piece of metal with that distinctive I-shaped profile. But this shape is the result of engineering genius, allowing a single beam to support loads of several hundred tons. A skyscraper being built somewhere in the world right now might contain a piece of armor plating from a warship, melted down and born again. This isn't just metal, it's history, sealed in steel. How does a mountain of rust become a precision structure with tolerances measured in fractions of a millimeter? And why is every modern building taller than a few stories impossible without this unassuming component? Stick around till the end. There's a moment we'll show you that's almost never seen publicly. The genius of the I-beam is in its shape. When it bends, the main load hits the top and bottom edges of the cross-section. That's where most of the steel lives, in those horizontal flanges. The thin vertical web in the middle, it just holds the flanges apart at the right distance. This gives you maximum strength with minimum weight. And that's exactly why this profile shows up everywhere you need to span a gap without wasting material. If you rolled that same volume of steel into a flat rectangle, it'd hold a fraction of the load. That I-shape isn't about aesthetics, it's math. One properly installed heavy I-beam can handle hundreds of tons. Picture a column of fully loaded semi-trucks standing on a single piece of steel. That's the real power of shape. But this story doesn't start in some gleaming factory. It starts at a massive, noisy yard that looks like a graveyard for metal dinosaurs. This is a scrap metal depot. Mountains of old cars, sliced up railroad cars, construction wreckage, and industrial junk, all waiting to be reborn. If stories about the hidden life of metal grab you like this, subscribe to the channel right now and hit that bell so every new episode lands straight in your feed. A giant crane with a powerful electromagnet descends onto this pile, and with a metallic screech, tons of old iron stick to it. This scrap is the main ingredient of the entire production process. It's loaded into a massive steel basket and sent to the melting shop, where a fiery baptism awaits. Steel is the absolute champion of recycling. The recycling rate for structural steel reaches 98%. That means practically all the metal from demolished buildings, old bridges, and scrap ships returns to production. On average, a new I-beam is 90% recycled metal. A skyscraper being built today might contain a piece of a car from the 70s, a railroad rail from the 30s, and armor from a World War II ship. This isn't just a piece of steel, it's compressed history, remelted for new service. This is the special magic of manufacturing that almost never gets talked about. The steel cycle is virtually infinite, and each generation of cities passes its metal to the next. Every year, the US alone produces over 5 million tons of structural steel, and most of it, I-beams. That scale is hard to wrap your head around, so let's try. The steel in the Golden Gate Bridge weighs about 83,000 tons, which means American mills produce enough beams in 1 year to build more than 60 of those bridges. 60 Golden Gate bridges, every year. And that's just one country. The heart of the mill is the electric arc furnace, a giant bucket the size of a small house where scrap metal gets dumped with a deafening roar. The sight alone is incredible. Tons of twisted iron crashing inside, filling the bucket to the brim. From above, 3 massive graphite electrodes descend into the furnace, each one as thick as an old-growth tree. The operator flips the switch. An electric arc flashes between the electrode tips and the metal, an artificial lightning bolt striking with colossal force. The floor fills with a deep, ear-splitting roar, and the light from the arc is so bright it blinds you even through protective glass. The temperature inside instantly rockets to 3,000 degrees Fahrenheit. The metal doesn't stand a chance. It starts melting, transforming into a boiling, blinding lake. Special additives get thrown into this molten bath: manganese, silicon, sometimes chromium or nickel, to create the exact grade of steel needed. Strong yet flexible, able to withstand massive loads without shattering like glass. The entire melting process takes 40 to 60 minutes, and in that time, tons of rusty junk completely transform into uniform liquid metal. Once the steel's ready, it needs to go from liquid river to something solid. The molten metal gets poured into a continuous casting machine. Glowing liquid flows into a special water-cooled copper mold. Passing through it, the outer layer of steel solidifies, forming a thin shell. From there, this still semi-liquid billet continuously gets pulled downward, passing through a water spray zone where hundreds of nozzles shower it with water, forcing it to solidify completely. Out of the machine crawls an endless, red-hot, massive steel billet, square or rectangular in cross-section. This is called a bloom. Automatic cutters hiss as they slice off pieces to the right length, 20, 25, 30 feet. This is our blank, the chunk of dough we're going to shape into a beam. Looks like an ordinary rectangular bar. No hint of the form it'll take in just a few minutes. These hot but now solid blooms head to the next furnace, the reheating furnace. Think of it as a giant tunnel with flames roaring inside. The blank creeps slowly through, and its temperature climbs back to the perfect working state, around 2200 degrees Fahrenheit. It becomes plastic and soft, like clay, ready for the most critical step, rolling. The quality of this heating determines just how precise and uniform the final profile will be. And now, the real spectacle begins. The bloom, heated to a blinding orange glow, rolls out of the furnace and enters the rolling mill. This is a series of gigantic steel rollers, like enormous rolling pins positioned one after another. But these rollers aren't flat. They have special grooves or calibers whose shape gradually approaches that of an I-beam. The bloom crashes into the first pair of rollers. They squeeze it with incredible force, thousands of tons, making it slightly thinner and longer. At the exit, the next rollers catch it, compressing it at a different angle and starting to form the flanges and web of the future beam. Step by step, passing through dozens of these roller pairs, the shapeless bar visibly stretches and takes on the familiar I-beam profile. A glowing chunk 20 feet long extends into a fiery ribbon stretching several hundred feet. The entire shop fills with thundering noise, the screech of metal, and the hiss of water cooling the rollers. This is one of the most powerful industrial spectacles you can witness with your own eyes. When the beam emerges from the final finishing roll, it already has perfect shape and dimensions, accurate to within 1/10 of a millimeter. Hot, long, like a fiery serpent, it travels along a roller conveyor to a massive cooling table. This giant grid is where the beam slowly cools down, releasing its heat to the air. This process can't be rushed. Cooling too quickly creates internal stresses in the metal that can later lead to deformation or microcracks, invisible from the outside. During cooling, the metal shrinks slightly, and sometimes the beam can warp just a bit. This is normal and predictable. Engineers account for this in the manufacturing process. To correct any deviation, the cooled beam is sent to a straightening machine. It runs the beam through a system of rollers that press with calculated force and squeeze out any deviation from straightness. What comes out is a perfectly straight steel profile, ready for final operations. Now we've got a perfectly straight beam, but it's not ready to ship just yet. Time for the finishing touches. First, they cut it to the exact lengths the customer ordered. Giant circular saw blades about 6.5 feet across do the job. With a deafening roar and a shower of sparks, The saw slices through thick steel in just seconds. Then, every beam goes through rigorous quality control. Inspectors check the geometry, while ultrasonic equipment peers inside the metal, making sure there are no cracks or internal defects. Only after that does the beam get its markings, basically a birth certificate with info on the steel grade, size, and batch number. Standard beams range from a few inches tall to almost 3 feet. But there are real monsters, so-called super heavy sections used in the most critical joints of skyscrapers. These beams stand over 4 feet tall and weigh up to 1,200 pounds per foot of length. Think about that. Every foot of one of these beams weighs as much as 3 grown adults. Standard lengths run 60, 80, sometimes even 120 feet. A single beam weighs as much as a battle tank. This is it. Born from rust, passed through fire and thousands of tons of pressure, it becomes the silent steel backbone of a building that'll stand for centuries.
Every year, dozens of nuclear submarines get retired around the world. Steel giants weighing over 10,000 tons. Inside each one sits a reactor pumping out hundreds of megawatts. But what happens when their service ends? How do you cut out the heart of a nuclear monster and survive a battle with invisible radiation that lasts for months? Temperatures here hit 14,000 degrees Fahrenheit. A mistake isn't measured in seconds, it's measured in centuries. In this video, you'll see the decommissioning process from the first cut to the last ton of melted metal, and find out what becomes of a submarine giant's armor. The process begins with the most dangerous stage, removing the spent nuclear fuel. The submarine is moved into a special enclosed dock. Around it, a real scientific laboratory unfolds. This is a battle against invisible radiation. It doesn't last days, it lasts months. Inside the reactor core are fuel assemblies. They've kept this monster alive for decades. Each assembly is a bundle of thin zirconium tubes, about half an inch in diameter. Inside, uranium dioxide pellets. One assembly is 13 feet long. Weight, 660 pounds. The reactor holds 100 to 120 of them. They're removed using remote manipulators. Each assembly emits a lethal dose of radiation, 500 roentgens per hour at 3 feet. That'll kill a person in an hour. The assembly is lifted by a crane rated for 20 tons and lowered into a lead container. Container wall thickness, 10 inches of pure lead. Container weight, 17,000 pounds. Only lead stops gamma radiation. The containers are loaded into special rail cars with water cooling and shipped to temporary storage. This stage takes 3 to 4 months of continuous work. If you're interested in seeing how things built for war get taken apart, subscribe to the channel. Here we show you production processes hidden from view. Once the fuel's extracted, it's time for the reactor compartment. This is a massive section of the sub. Weight, 1,500 tons. Length, 33 feet. Diameter, 30 feet. Engineers don't dismantle the reactor piece by piece. Too dangerous. The metal itself is radioactive. Neutron flux from the operating reactor bombarded the steel for years. Iron atoms transformed into radioactive isotopes, so they cut out the entire compartment whole. They use oxyacetylene torches. Flame temperature 5,800 degrees Fahrenheit. Mix of acetylene and oxygen. Feed pressure 217 pounds per square inch. The torch burns through 3-inch thick steel in 10 minutes. They cut in a ring around the compartment. 2 cuts, forward and aft. You get a cylinder. All technological openings are welded shut with half-inch steel plates. Welding, electric arc, 1/4-inch diameter electrodes. Current, 350 amps. You get a sealed capsule. It's lifted by a 200-ton crane and loaded onto a barge. The barge is towed to a burial site. In Russia, that's Novaya Zemlya. In the US, Hanford site. There, the capsules are placed in concrete trenches 65 feet deep, covered with earth on top. They'll sit there 300 years until radiation levels drop to background. Decontamination is the longest phase. The reactor compartment's cut out and shipped off, but the work's just beginning. Decades of coolant circulation left their mark. Thousands of feet of primary loop piping, pumps, heat exchangers, steam generators, all of it contaminated. Radioactive isotopes soaked into the metal. That's induced radiation. Teams in protective suits scan every foot, hunting for hotspots, areas with elevated readings. They use DP5B dosimeters. Sensitivity, 0.01 milliroentgen per hour. Every pipe gets checked, every pump, every valve. Then chemical flushing begins. They run acid solutions through the primary loop piping. Sulfuric acid at 10% concentration. Temperature 140 degrees Fahrenheit. Pressure 115 psi. The acid dissolves the oxide film off pipe walls. Radioactive isotopes go with it. Solution gets collected in 13,000-gallon tanks, filtered through ion exchange resins. Radionuclides precipitate onto the resin. Resin gets incinerated at 2,200 degrees Fahrenheit. You get ash. Mix the ash with cement and pour it into concrete containers. That's Class II radioactive waste. Chemistry doesn't work everywhere. Valves, gate valves, filters, they dismantle those by hand. Teams of 3. Shifts last 30 minutes. Can't go longer, the dose accumulates. Every part gets packed in a lead box. Box weighs 265 pounds. Walls, 4 inches of lead. If contamination levels run too high, they encase the part in concrete right inside the hull. Special attention goes to the reactor's biological shield. Massive plates of lead and polyethylene. Lead layer, 6 inches thick. Polyethylene, 12 inches. Lead stops gamma rays. Polyethylene slows neutrons. Weight per plate, 4 tons. 8 plates total. They pull each one with a crane. Decontaminate with ultrasound. Frequency, 40 kilohertz. Power, 3 kilowatts. Ultrasound breaks down the oxide film. Then they rinse the plate with alkaline solution and dry it with hot air at 250 degrees. Only after thousands of air samples and surface swabs, when everything reads 0, they open the dock to regular workers. Now it's not a nuclear facility, it's just a complex steel structure. Cutting the hull. After decontamination, the submarine is ready for final dismantling. The submarine's hull isn't ordinary metal, it's an alloy built for war. It withstands water pressure at depths of 1,000 to 1,300 feet. That's 30 to 40 atmospheres. Hull thickness, 3 to 4 inches. A K29 grade steel. Tensile strength, 100,000 pounds per square inch. Regular cutters won't touch it. They use plasma torches. Plasma is ionized gas. An electric arc creates the temperature. Voltage, 300 volts. Current, 400 amps. Power, 120 kilowatts. Argon gets blown through a nozzle 1/8 inch across. Pressure, 90 pounds per square inch. Flow rate, 1 cubic foot per minute. The arc heats the argon to 15,000 degrees Fahrenheit. That's 1.5 times hotter than the surface of the sun. The plasma jet shoots from the nozzle at 670 miles per hour. That's the speed of sound. Under that stream, 4-inch thick steel melts in 5 seconds. The torch follows the marked line. Cutting speed, 8 inches per minute. Sparks and smoke fly from the torch. Flame height, 10 feet. Spark temperature, 1,800 degrees. The second tool, oxygen lances, a 10-foot steel pipe, 1-inch diameter. Inside, a bundle of steel rods, each about 1/6 of an inch thick. Pure oxygen flows through the pipe at 150 psi. Flow rate, 50 cubic feet per minute. The rods are ignited with an acetylene torch. They start burning in the oxygen. Steel burns. Massive amounts of heat pour out. Temperature in the burn zone, 6,900 degrees Fahrenheit. The lance burns clean through the steel, leaves a molten seam 2 inches wide, burn through speed, 20 inches per minute, faster than plasma. But it takes serious skill. You guide the lance dead perpendicular. Deviate more than 10 degrees and the burn's incomplete. Crews of 4. Protective suits made of Kevlar. Masks with number 13 filters. They block infrared and ultraviolet radiation. Without the mask, your retina burns in 1 second. They cut from bow and stern, working gradually toward the center. The hull gets cut into cylindrical sections, each section 20 feet long, 30 feet in diameter. Weight, 400 tons. Cranes rated for 800 tons lift the sections and stack them in the sorting zone. Metal sorting. Every hull fragment gets checked again with dosimeters. They're hunting for isotope traces in microcracks and weld seams. If the device clicks, the fragment gets isolated, sent for re-cleaning or special disposal. Only clean metal receives a safety certificate. It can leave the shipyard territory, then sorting by chemical composition. Steel grades HY80 and HY100. These are high-strength steels. Nickel content, 8%. Chromium, 2%. Molybdenum, 1%. These alloying elements are treasure for metallurgists. Nickel provides toughness. Chromium, corrosion resistance. Molybdenum, strength at high temperatures. Regular hull steel. AK-29 gets sent for remelting separately. Titanium parts, the sail, fairings, also separate. Titanium doesn't melt with steel. Different melting points. Titanium, 3,034 degrees Fahrenheit. Steel, 2,795. Copper alloys, wiring, heat exchangers, to non-ferrous metal. Aluminum alloys, bulkheads, ladders, to aluminum scrap. Reborn in fire. High-strength steel heads to the metallurgical plant. Loaded into an electric arc furnace. Capacity, 100 tons. 3 graphite electrodes, 24 inches in diameter. 600 volts, 60,000 amps. 36 megawatts of raw power. An arc ignites between the electrodes and metal. The arc zone hits 6,300 degrees Fahrenheit. Metal melts, becomes a liquid lake. The melt reaches 3,000 degrees. Melting time, 3 hours. Lab techs pull samples every 30 minutes. Analyze composition on a spectrometer. Adjust with ferroalloy additives. Precision matters. Carbon tolerance, plus or minus 0.05%. Nickel, plus or minus 0.1%. Finished melt pours into a ladle. The ladle weighs 200 tons. From the ladle, it flows into molds. Create slabs, steel plates. 6.5 feet by 20 feet. 10 inches thick. 23 tons each. Slabs get rolled into sheets or cut into rebar stock. Yesterday's warship armor plating becomes a river bridge support or a skyscraper skeleton. Steel that once withstood depth charges now holds up bridges. Metal doesn't die. It lives again. If you found this fascinating, hit that like button. Drop a comment. Did you know submarines get recycled for 300 years? Subscribe. We show you how the old dies and the new is born. Ever wonder how you make a material just 6 microns thick? That's 15 times thinner than a human hair. So thin that if you hold it up to the light, you can read a newspaper through it. So fragile that one wrong move and it tears. Yet so strong it can withstand temperatures of 570 degrees Fahrenheit and protect your food from light, oxygen, and bacteria better than any plastic. I'm standing at the gates of the Eurofoil plant in Dudelange, Luxembourg, one of the largest aluminum foil manufacturers in Europe. Here, across 50 acres, 100 tons of foil are born every single day. That's over 600 million feet, a ribbon you could wrap around the Earth 5 times at the equator. The air is thick with the smell of hot metal and machine oil. The roar of the rolling mills is so powerful the ground vibrates beneath your feet. Welcome to the place where aluminum makes the journey from crude ingot to an almost invisible film. This isn't just a factory, this is a laboratory of precision at the edge of what's physically possible. process begins in the foundry where real metallic hell reigns. 4 continuous casting machines run non-stop 24 hours a day, 365 days a year. I put on protective goggles with dark filters. Without them, looking at molten aluminum is just dangerous. The temperature here stays at 1330 degrees Fahrenheit. This is the melting furnace where they load aluminum ingots, massive bars weighing 55 pounds each. But Eurofoil prides itself on being eco-friendly. 70% of the raw material here is recycled aluminum. Foil scraps, production waste, even old soda cans, everything gets used. Aluminum can be melted down infinitely and it doesn't lose its properties. Jean-Pierre, the plant's head metallurgist, shouts in my ear. We're standing on a platform above the furnace and the heat is so intense that the skin on my face starts tingling. In the enormous crucible, a silvery liquid churns, molten aluminum. But this isn't just pure metal, it's an alloy. Depending on the intended purpose of the future foil, they add magnesium, manganese, silicon. For food-grade foil, alloy 8011. For technical foil, alloy 8079. Each percentage of additive changes the properties: strength, plasticity, corrosion resistance. From the furnace, molten metal flows into the casting machine, a 100-foot-long monster. Here's where the magic happens. Liquid metal at 1300 degrees turns solid in seconds. This is continuous casting. Molten aluminum pours between 2 rotating water-cooled rolls, 6 feet across. Inside those rolls, water circulates at 150 pounds per square inch. When scorching aluminum hits cold steel, instant crystallization. The sound? Like dumping a bucket of water on a blazing stovetop. Hissing, crackling, clouds of steam. Out from under the rolls comes an aluminum ribbon, 1/3 of an inch thick, 5 feet wide. It's still glowing dull red, around 750 degrees. The ribbon crawls forward at 10 feet per minute, slowly cooling in the open air. I step closer and watch as a distinctive pattern emerges across the metal surface. That's the crystalline structure of aluminum. Metallurgists call this grain. Everything depends on the size and shape of those grains, how well the foil will stretch, whether it'll tear during winding, how it'll behave under heat. The perfect grain is a labyrinth, Jean-Pierre explains. The crystals need to interlock with each other, creating a strong network. If the grain's too coarse, the metal becomes brittle. Too fine, it loses flexibility. The cooled strip winds into giant coils weighing 12 tons each. These are blanks for the next stage, hot rolling. We move to the adjacent shop, where rolling mills stand as tall as a 2-story building. Here they start rolling the aluminum strip like dough, except instead of a rolling pin, 50-ton steel rollers, and instead of a table, an alloyed steel frame 3 feet thick. They feed the coil into the mill. The rollers spin, grip the strip, and pull it through with monstrous force. Pressure hits 1,200 tons per square meter. The metal resists, springs back, but gradually gives in. After the first pass, thickness drops from 8 millimeters to 4. After the second, down to 2. Speed builds. If at first the strip crawled at 5 meters per minute, after the third pass it's flying at 300 meters per minute. Air whistles. The strip hums like a taut string. Each pass generates massive heat. Metal grinding against steel heats the strip to 250 degrees, so the rollers get continuous cooling emulsion, a water oil mix. It sprays at 30 atmospheres of pressure, forming a white cloud of mist through which the strip shoots like silver lightning. After hot rolling, the strip, now 0.12 inches thick, heads to annealing. This step is critical. Here's why. During rolling, aluminum work hardens. It gets tough and brittle. The metal's crystal lattice deforms. Internal stresses build up. Keep rolling without annealing. The strip just tears. The annealing furnace is a tunnel 260 feet long. The strip travels through at 33 feet per minute. Inside, the temperature hits 930 degrees Fahrenheit in a nitrogen atmosphere. Oxygen is completely excluded. Otherwise, the aluminum oxidizes and gets covered in loose black scale. At that temperature, recrystallization happens. The metal's deformed grains heal. Internal stresses release. The aluminum goes soft and ductile again. This process takes 2 hours. Coming out of the furnace, the strip cools in a water bath, then gets dried with hot air. Now it's ready for the most demanding stage, cold rolling to final thickness. The cold rolling mill. That's the heart of the factory. 3 state-of-the-art rolling stands here, capable of rolling aluminum down to 6 microns thick. That's the limit. Any thinner? Physically impossible without tearing. The process takes 20 passes. Each pass reduces thickness by roughly 30%. 0.12 inches becomes 0.08, then 0.06, then 0.04, and so on, until you hit 0.0024 inches, 6 microns. Rolling speed on the final passes? 67 miles per hour. The foil ribbon flies faster than a car on the highway. The slightest vibration, the tiniest roller deviation, and it tears. A tear at that speed means shutting down the entire line, losing several tons of material and hours of rethreading. That's why laser thickness gauges are installed here, measuring the strip 200 times per second, accurate to 0.4 microns. The computer instantly corrects roller pressure, rolling speed, coolant flow. A human couldn't react fast enough. I'm watching the monitor in the control room. The thickness graph runs flat. 6.0 microns, 6.1, 6.0. Deviation within plus or minus 0.8 microns. That's perfection. But there's a problem. You can't roll foil 6 microns thick in a single pass. It sticks to itself, tears, crumples. So they use a clever trick, doubling. 2 layers of foil, each 12 microns thick, are stacked together and rolled as one. The rollers press down, and both layers simultaneously thin to 6 microns. But between them remains the thinnest air gap. After rolling, the layers are separated. And here's where an interesting effect shows up. One side of the foil, the one that contacted the roller, comes out, shiny, mirror-like. The other side, which contacted the neighboring foil layer, stays matte. You've probably noticed this on kitchen foil. Well, it's not a defect and not a special coating. It's the trace of the doubling process. The matte side is the imprint of the microtexture from the adjacent sheet. At the molecular level, it's covered with microscopic irregularities that scatter light. The finished foil gets wound onto huge jumbo rolls, 6.5 feet across and weighing 3 tons. These are the mother rolls. From them, they'll later cut foil to the needed width. For chocolate wrapping, 12 inches; for yogurt lids, 2 inches; for industrial uses, 4 feet. Quality control at Eurofoil borders on paranoia. And that's a good thing. Every jumbo roll goes through a dozen tests. First up, backlighting. The foil passes in front of a powerful lamp. Any microcrack, any pore, and light will shine through. A computer flags the defect, and that section gets marked as scrap. Second, leak testing. A foil sample gets clamped between 2 chambers. Helium under pressure is fed into one, A highly sensitive detector sits in the other. If even a single helium molecule seeps through the foil, test failed. Third, mechanical testing. The foil is stretched on a specialized machine, measuring tensile strength. Quality foil must withstand a load of at least 15 megapascals. That's roughly 330 pounds per square inch. For a material 6 microns thick, that's a phenomenal number. Fourth, chemical analysis. Every 2 hours, they take a sample and run it through a spectrometer. It shows the exact alloy composition down to hundredths of a percent. Any deviation, and the batch goes back to the smelter. Fifth, corrosion testing. A sample is held in salt fog at 95 degrees Fahrenheit for 72 hours, simulating 3 years of use. If corrosion shows up, it's scrap. The final stage, slitting and packaging. Jumbo rolls feed into slitter rewinders. Disc blades made from hardened steel, sharpened to razor-edge sharpness, cut the 10-foot wide web into narrow strips of the required width. Slitting speed, 1,600 feet per minute. Blades spin at 3,000 revolutions per minute. The slightest wobble, and the foil edge comes out ragged, jagged. That's why blades get swapped every 8 hours. Slit rolls move to winding. Here the foil winds onto cardboard cores 3 inches in diameter. For household foil, the standard, 33 feet per roll. For the food industry, rolls of 1,000 feet, 1,600 feet, 3,000 feet. An automatic system measures the required length, cuts, seals the edge, marks the roll with a barcode. Output, 200 rolls per minute. Finished rolls get packed into cardboard boxes, boxes loaded onto pallets, pallets hauled to the warehouse. From here, Eurofoil foil ships to 70 countries worldwide. To Germany for chocolate wrapping, to France for cheese factories, to Italy for coffee capsules, to Switzerland for pharmaceutical blister packs, to Japan for electrolytic capacitors. I'm standing in a finished goods warehouse. Around me, stacks of pallets tower 13 feet high. Each pallet holds 2,000 rolls of household foil or 50 jumbo rolls of industrial grade. The product stored here is worth around 5 million euros. The plant runs at full capacity. 100 tons of foil per day, 3,000 tons per month, 36,000 tons per year. That's enough material to wrap the entire United Kingdom in a continuous sheet, or package 15 billion chocolate bars, or make 300 billion yogurt lids. This entire foil empire was born from a simple piece of aluminum that passed through the inferno of casting furnaces, the monstrous pressure of rolling mills, the precision of laser measurements, and rigorous quality control. From 8 millimeters down to 6 microns, a journey 1,300 times over. If you found it interesting to learn how a material thinner than a human hair but stronger than many plastics is created, hit the like button on this video. Write in the comments whether you knew that aluminum foil can be recycled infinitely. And subscribe to the channel to keep discovering the technologies that surround us every day but remain invisible.